to everyone that we're cheating.
Okay.
Yeah.
Awesome.
Great. So, I guess, does anyone still need the meeting flag? Yes.
About something that you said on the previous slide. You said what was on the left?
This is from Guided Hacking. It's like a thumbnail, and it's like a video on like trampoline hooks. So I'll cover it later. But so essentially, they were showing you how to like write the inline assembly to perform raw hooks.
Is it like a YouTube video?
Yeah, it was like a YouTube video. So what is game hacking? And it's the practice of reverse engineering, modifying video game software to manipulate game behavior. And this involves like memory manipulation, code injection with like DLLs, which we'll get into. Requires a lot of reverse engineering because like you can imagine if you ever done like blind pwn, game hacking is just all blind pwn but worse. Actually, it's not as bad. You don't have to craft payloads blind, but like it's a blind challenges. And then anti-cheat evasion, which I find the most interesting because you can do some pretty stupid stuff to just get around like the detections from anti-cheats. And then that's like tool's cheat engine, and it's a like classic tool to like perform like typically you'll like edit memory with it, or you can like scan for specific like values like your money or your health, and then you can actually change that in cheat engine. It's a very useful tool. So first we're gonna have to like go over like the Windows executable file format. So you guys have probably raise your hand if you've like taken CS128 or you're taking it right now. So that class covers like C++, but then they do everything inside like a Docker container, which actually compiles down to Linux binaries. So most of like your experience with like Azure sanitizers and stuff is going to be with Linux binaries. In fact, like most CTF challenges, if it's like pwn, is going to be on Linux binaries. But they use a thing called ELF, which is like the executable Linux format or something like that. And then you have Windows portable executables, which is Windows PE. You can see that there's a decent amount of difference in like the way that they structure their binaries. So you have the ELF header, the program header table, and then a bunch of other sections inside of ELF binaries. And then with PE binaries, you have the DOS-MC header, PE header, and then your section table. And then relatively else, you just like have your sections underneath that. And then your section header table, of course, points and like it says like how big each like section is of your like binary. And then our data is like read-only data inside of the PE binary. And then yeah, .text stores executable code. And that's pretty important because if you want to, for instance, if you wanted to put shell code into a game, it needs to be executable. And a lot of like anti-cheats will hook like if you can change memory protections on Windows, so you could make specific sections of memory executable, but then certain anti-cheats can actually like detect the syscalls that are being made to do that, and they'll just ban you from their game. So the DOS-MZ header, it's not really important for this, but it contains a pointer to the PE header, and this is really important if you're doing something called manually mapping DLLs, because you're going to have to find your PE header in memory, and first you do that by finding the DOS-MZ header. And there's a specific signature or like some magic bytes that like identify the start of the DOS-MZ header, and then from there you kind of cast that into structs that you use in order to manually map a DLL. We're not going to get into that today, but I think Ronan might get into like showing manual mapping later.
Yeah, I initially looked at that on Tuesday.
Yeah.
So I'm sure. Like, just curious, do you tend to stomp out MC header after mapping?
Yes. Okay. Yeah. So, like I do that. I unlink from the ped, etc.
Yeah, right.
So. Well, it's to remain undetected, right? It's like the whole goal of this is to like, well, guys, don't go around like I can't condone cheating in games, but if you the whole goal of game hacking is sort of like evade the anti-cheat systems or sort of like get around the protections they put in place, and then sometimes they'll be able to detect some of the methods that we teach here today, but there are ways to get around it. So then the PE header is where like a lot more interesting stuff happens. So it specifies like your sections and stuff. But most importantly, it has the import and export table for DLL functions. So if you can imagine, like, for instance, if a game had like do you guys know what DLLs are? Or so DLLs are shared libraries. I'll get into it a bit later. But so like essentially it's code that is shared across multiple like executables. Like for instance, kernel32.dll is what's called a shared library. So that contains like specific functions that are essential to run a program on Windows. And like multiple executables can call upon that code and run those functions inside of it. That's like sort of like the high level overview of that. And the PE header, it also, it gives us the important functions to hook, but it also gives us the base address of the image. And this is really important because most of the time, games will have like ASLR enabled. So your addresses will be randomized and you'll have to like actually, because the executables are what's called PIE, which is position independent executable, which means that they can just like shift their addresses in their code so that it's just like completely random. So you can't just, for instance, call the same address twice across 2 runs and expect it to point to the same thing. Yes.
What does ASLR stand for?
Address space layout randomization, if I believe. And so that's sort of like how, if you go here, actually, I think I have a diagram on the next slide. Maybe not. So, or yeah, right here. So as you can see here, Windows sort of has like a different address layout than Linux. As you know that like in Linux, your heap and stack addresses tend to be at a lot higher addresses. In Windows, they tend to be at a lot lower addresses. And then specifically right here is where your program image is stored. And so for instance, if we wanted a pointer, so a pointer is essentially, it's a variable that contains an address. And these addresses point to specific points in memory, right? It defines like specific like parts where your executable has like, it stores its data, right? You can index it using an address. So this right here, you might not always be able to, for instance, assume that the base address of your like code in memory is going to be 0x04 and then all those zeros. You can't always assume that because of ASLR. Very simple way to get around it, specifically because how many of you guys have gone to like Pwn 1 or Pwn 2? So you'll probably know that if with ASLR, it's kind of really annoying when you're writing shellcode. But since we're writing our own code, we can actually call some Windows functions that allow us to actually get our base address relative with ASLR enabled. So 2 things, there's x86 binaries and x64 binaries. And x86 binary has a 4 GB address space, and then 64 bits is just absurdly large. You have 16 exabytes worth of address space. And what's really interesting here, right, is that this is your memory layout, and you can see that you have DLLs inside here. So your DLLs are mapped inside of the same memory space where your executable is, and that'll come to be really important later. And then also notice that we have the PEB and the TEB. So the TEB stores like the like sort of like thread information, and the PEB contains like a lot of process metadata, and also like tells you like what DLLs are imported. And you have like there's like a table inside the PEB which tells you like what DLLs you have imported. So that could be like a detection vector from anti-cheats. If we wanted to put our own code into there through a DLL, they might be able to detect that by checking the PEB. Yes.
So when it comes to using the DLLs, really all our programs, if you go back, all of our programs will be running in that stack heap program image, like upper half in this example.
Yes.
And then they would be all universally calling the DLLs, which are like almost immutable or like universal state.
Yeah, so these are sort of, so actually like the DLLs aren't like in memory. They're not like, you can't just access a DLL from an arbitrary point in memory. We have to actually load it into the actual program's memory because it's virtual memory. Because like the processes have isolated memory from each other. So we actually have to load the DLL from disk and put it into memory to be able to execute the functions inside of that shared library.
So would they be calling the DLL code then, or like executable data from that portion of memory or from the actual like program memory?
So essentially what will happen is that in your program image, you'll have, well, it abstracts down to this, but if you load a DLL into memory, you essentially, or you have access to, you can read memory from the DLLs, and there is like readable, and this is on a DLL space. So from the program image, you're actually calculating like where is this DLL in memory, right? And then you calculate the address of a specific function in there, or you can look up their function name by the symbol name.
You're not doing copy there. You're just reading it.
Yeah, so you're essentially just using an address. You're finding the address of a function inside of a DLL, and then you're essentially that address is like the start of a function. I'll get into function pointers a bit later, but essentially you're calling those functions through function pointers because it's stored in your address space, and you're calling it from your program image, and it's referring to this part of memory. So one very rudimentary way of game hacking is just patching the executable. I think Ghidra and like Binary Ninja and IDA all support this. Where it's essentially you can just change like the actual assembly code. How many of you guys went to the assembly meeting? Yeah, so essentially you can overwrite the assembly inside of your binaries to do what you want. So for instance, you have targets like jump equal to or jump not equal to. So I don't know, did you cover these? Did you cover jump equal to and jump not equal to?
A little bit.
So this is sort of like conditional, like these sort of are like conditional operators in assembly, and essentially it's saying like if a specific value is equal to another one, then jump to a specific point, like jump to a specific part of your binary or jump to this other part. So essentially, if you can imagine it this way, we can change a JE to a JNE, which means that we can flip, like if you had a program that was like in like C++, for instance, or even in Java, like it was like if 0 is equal to 0, that would return true. And that would be a jump equal branch, right? You would do like whatever is inside of that if statement with a jump equal branch. But if you wanted to flip it so that maybe like the stuff that's in that branch never happens, the contents of that if statement never occur, you can change that to a jump not equal to, or you could just completely do what's called knopping it, is what I refer to it. And that essentially just means that you replace that assembly code with dummy code, so it just never happens, right? You never even check if these two values are equal to each other. Another thing is that you can patch constants inside of like a static binary. So like, for instance, if you are storing like health as a static variable, that's stored inside of the program image, and we can just simply edit that value, that static variable, and it'll change it. So like, for instance, if we had health as a static variable, we could just simply change like our health to be like 1,000,000, and then nobody can really kill us. So there's two types of cheats that I'll get into. We have external cheats and internal cheats. If I'm going a little fast, just let me know. And if you have any questions, just raise your hand. But external cheats generally run as a separate process. You're not injecting any of your own code into like a game, for instance. You're only doing external read and writes from a different process. So the three essential functions for external cheats is read process memory, write process memory, and virtual protect. So essentially read process memory allows you to, if you have the specific address inside of like a different process, you can query its like virtual address space and read specific bytes of memory from there. And then write process memory, you can just like if you have like an array of bytes, right, and you have a target location you want to write that to, you can just write like if you, for instance, if you had a string in a separate program, you could use write process memory to overwrite that string in that program, and then every time like it prints out that string, it'll print out like that string that you replaced it with. And then virtual protect. So again, there's like specific sections of memory that are read only and you can't write to it. And sometimes they'll store like stuff like maybe like your user ID and read only memory. And maybe you want to change that for whatever reason. So you can use virtual protect, which allows you to set, for instance, your like that specific portion of memory to be writable. And then immediately after you set it to be non-writable after that, this is like sort of like a big detection method because you can tell when memory like permissions have been changed from like a lot of entities can tell. So it's generally you should try to avoid virtual protect unless you know what you're doing and know how to like bypass specific protections that entities are putting in. One thing about external cheats is that they're a lot harder to detect than like injecting your own code into a game process. That's specifically because like there's only like 3 surfaces for you to detect it, is like these 3 functions for the most part. Of course, they can like scan like processes for signatures, and I'll get into that later. But generally, if they're detecting read process memory, write process memory, or virtual protect, that's only really 3 things you have to figure out. How do I get around this game detecting me using these functions? Yes.
Just to ask, why is it harder to detect? Because those are the only 3 API calls I need to inject with anyway.
That is true. So it's generally harder to detect because you're not really loading anything directly into their memory. So the process isn't, it takes a lot of resources to go down a process list and scan the memory instead of like individual processes. But then if it's sort of like you inject your own code into the own like a process, they can just scan its own memory, its own address space, and then it'll signature scan you and find like you have a DLL injected in here somewhere. You are right though, we do have to use write process memory and virtual protect to inject a DLL. But again, there's like ways to get around like these methods being detected. But it's generally harder to detect relatively to internal cheats, right? You can detect internal cheats in a similar way by detecting this. But like, for instance, if you were to use a kernel driver to write to a process memory, it's not going to know. So internal cheats is where things get really interesting. So these actually run inside the game process. And they can call functions like spawn items, teleport. So like if you have like a function that you write in like C, like what if you say like teleport and then like to some coordinates, right? To move the player to some like point in the game. You can actually call that for yourselves and just arbitrarily teleport yourself anywhere. And that's like what makes this really powerful. You can also hook functions. So that is like, we'll get into hooking later, but for instance, if I wanted to know every time that I'm being attacked, right? Like I got hit, let's say that decrements my health. If I could sort of like intercept that, right? That being called like you got damaged, I can hook that and then maybe I can do whatever I want with it. Maybe I can set it so that I took negative damage, for instance, and that would actually increase my health instead of decreasing it. You can do some really powerful things with hooking. And then one thing is that you can access memory through pointers. So for instance, you can reinterpret like, this is like just for instance, an arbitrary address in memory. You're not compensating for ASLR or anything here. There's just like a high level overview, but imagine there's a variable stored at the address 0x dead beef. And let's say that that's like FF, right? FF is stored there. And that's like a byte that's stored at that specific address. The std uint8_t, that's an unsigned 8-bit integer type, which is in other words just like const char. If you're like taking CS128, like a const unsigned char pointer is what this really expands out to. byte of memory. And we can dereference that, and then this whole thing would return whatever is inside this address. For instance, it was FF, it will return FF. We can also set that using the dereference operator in C++. So we can set whatever memory or like byte is inside 0x dead beef to be like CC or whatever we want. Does anyone have any like questions about that? Or if you haven't taken CS128 yet, this will make a lot more sense once you take it. And then one of the downsides about making internal cheats is that it requires a lot more reverse engineering, right? So you'll have to like, it's like a blind pwn challenge. You have to like, in pwn, you have to find addresses of specific functions, but most of the time you'll have like symbols and stuff, so you kind of know what's going on in the binary. With a lot of games, they strip the symbols from their games, so you have to like actually just go line by line in like your assembly, or if you're not a Giga Chad, you can go down your pseudo C that's like generated by a decompiler, and go line by line and analyze, okay, what is this program doing? And you can find specific addresses of functions from there. But these functions are just going to be like, have mangled names because they have no symbols because they're stripped from the binary. And again, these are like easier to detect because people with internal cheats, you're injecting your own code into another process's memory. So they can just go down and scan their own memory using what's called like a signature scanner. I'll show you code of what that kind of looks like later, but you can also accelerate using a thing called AVX512, which is a x64 extension. So this just makes it stupidly fast. You'll get like instantly signature scanned if they're using an AVX512 accelerated pattern search. Yes.
That's what are the signature? That's not what signature like the code itself. Are the signature injected code or like hooks it in?
So for the most part, they're going to be signature scanning, like maybe like a game company, right? They saw like, all right, there's people that are injecting this code into my game. I'm going to look through this code and find parts of it that look unique that I'm like, I'm never going to put this into my code. And they'll do what's called creating an array of bytes. And it's a byte signature. So it will look like just like a array of hexadecimal numbers. And from there, they'll go down the process memory and then they'll see if there's a match for that like specific array of bytes in memory. And then if there is, then they'll just like flag you as like, it'll detect you and then kick you out of their game. Does anyone have any questions about that? I kind of like didn't really explain that very well. So here's one example with what you can do with hooking. So this is back when Roblox used to have a really bad anti-cheat and you could just willy-nilly inject any DLL into it. I actually think I was doing this on Mac OS. I just modified the example code to be for Windows. So right here, you can see we're calling this function get module handle null pointer. What that's doing is if we go back to our diagram here, we have this program image, right? And that's where all of the game's functions are stored. So if we want to know like, all right, so like the functions are stored, like you can assume like on a high level, it's sort of like stored in like a list, right? You want to know like where in memory does that list start so I can start calling these functions. So what get module or what get module handle null pointer does is it gets the base address of the program image in memory of the specific executable, right? And then right here, we have just an arbitrary address, and you'll find this through reverse engineering. And right here, this is what's really special about this is that we're performing what's called like a function pointer cast. So essentially, what this is that we're assigning message out to be a function that returns an 64-bit integer. As the first argument, it takes in a 32-bit integer that's unsigned, and then some string, and then it's also a variadic function, so it'll take in like any amount of registers after that, and then like your stack to have like any arbitrary amount of extra arguments. So with this pattern, right, I did put it inside of like the template DLL that I'll show later. You can call message out. So essentially from our DLL, you're able to call functions inside of games. Out is a function that's internally stored in Roblox is binary. And we're essentially saying that this specific address is the start of that function, and we can call that function now. So like we have message out 0 hello world. If you do a little reverse engineering on Roblox, you'll see that this message out function, the first argument is actually an enum, and 0 just means like information, right? Or like the standard print. And so we can call that. So like what this is saying is that we're gonna call message out with like a standard print color, because like if it was like, for instance, if this number was like 1, this text would show up as like blue, for instance. And this demonstration here is sort of applying hooks. So there's a lot of ways to apply hooks. I'll get into that later, like how to apply a raw hook. But there's a lot of libraries to use. Hook is like a sort of a cross-platform hooking library. And that essentially means that you can intercept when a function is being called and then analyze the arguments in it and then sort of call that function with some new arguments, or maybe you just want to terminate the call altogether. So you don't want that function to run at all. So essentially right here, we have to store the original message out pointer, because what this is that when you're hooking, you're essentially, the control flow of your program goes from your game memory. When you apply a hook, it goes to your DLL's code, right? With the function arguments. It calls our own callback right here. Yeah, it will call our own callback. It's not shown here, but I do have, I believe it's message out hook, and it's a function with the same signature as there. It's returns a 64-bit integer, takes in an integer, const char. And so essentially we recreated like the same function signature in our own memory. And so it goes from, in this case, Roblox's code to our DLL code. And then we process the specific arguments and such. And then we're able to go back to this message out original. And Dobby hook right here is going to be setting message out original to the actual function pointer. So this address plus like 8 or something. I'll get into the reason why we are adding to this specific address later. But so essentially we're going from Roblox's code to our code and then back down a little bit deeper into the function, right? And then continuing execution back in Roblox's code. But then we could have, in that time, injected our own arguments into that function. So what's actually, so like for instance, right here, what's actually happening is that we have hello world, because we call it this first time. And then the second time we called hello world after applying this hook, I think I made this hook specifically return, or it changed the second argument to always be hooked. And then right here, we're destroying the hook. So that just means that we're undoing the hook, and then we're no longer intercepting the calls to that function. And so that's why we can print hello world again. Does anyone have any like questions about like sort of like that on a high level? Yes. I'm sorry? So the sleeps are for hook is a very slow library, right? So you can have a race condition here actually, where hello world would have been printed twice, because hook runs this hook application in a separate thread. So you'll just have a race condition, and then maybe when you call it like immediately after, maybe the bytes weren't patched yet in order to actually like intercept the calls.
Why is it so slow?
It's very slow because writing to memory is very slow, right? Your CPU is able to execute instructions a lot faster than you are able to like sort of like read memory. That's why you have like CPU cache, for instance. Did you have a question?
So at a high level, you're printing out, overwriting to kind of add this hook so that you can print out something when you receive like a hello world, like print command, and then you reverse it back to it.
Yeah. So essentially what I'm doing right here is I'm just displaying that we can, this is like demonstrating two things, is that we can call specific functions in a program. We can apply a hook to a function in there, and then we can destroy that hook. And so right here, I'm calling message out from within my own DLL. But if Roblox, for whatever reason, also called the message out function, then it would also print hooked if it happened between like these two blocks of code. So one big thing about game hacking is that you're gonna have to do a lot of reverse engineering. One thing that can make your reverse engineering life a lot easier is that Ghidra and like Binary Ninja have tools to or sort of like reverse engineer structs. So if you take CS128, you'll learn about sort of like structs, but in our case, in memory, it's just sort of stored as like consecutive values that are like storing specific data. So like in memory, you might see like at a specific address, you'll have like maybe a pointer to a player's name. And then the second value, like that address plus like 8 would be like, for instance, like the player health, and then add another 8 to that. And that might be like the player X coordinate, for instance. So from here, you can sort of see that in memory, right? Structs store like as like specific offsets from a base pointer. So right here, num underscore 50s would be like if we created a new struct in memory, this is stored at a specific address, and at that specific address we'll have the value of num 50s, and then that address plus 4, because this is a 32-bit integer, will be storing num 100s. So right here, you can see this is the pseudocode of a OSU gaming CTF challenge called Tosu. It really made me crash out, but it required a lot of reverse engineering. So right here, you can see that we have this data and then this address, right? Let's just call that data for now. And then data plus 0xc. And then we see that, okay, we have a format string. And it's calling it with %d, 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 %d. So these are all like numbers. And the first argument here is the same data plus 8. The second one's plus 4. The second one is plus 0. And then the third one was referring back to this variable, which is storing the data of that pointer plus 0xc. So from here, we can actually reverse engineer the struct because we can match out, okay, 300 is being printed out, and then that's right here. And the first argument to this function is data plus 8. So intuitively, we can say, okay, this thing plus 8 is 300. And then the same goes for the rest of these. Yes.
The data thing is not strong.
We reverse engineered it. So with this struct, I had to create it in Binary Ninja. And essentially, I'm sorry?
You created it.
Yes, I created this struct using Binary Ninja. I think Ghidra also allows you to create structs. And essentially what that allows us to do is make our pseudocode a lot cleaner. Because right here, this is just like the raw pseudo C code. And it's just, you're dereferencing an offset from a pointer. That's not very human readable, not very specific at all. But if we reverse engineer, because originally, right, in the source code for Tosu, for this specific challenge, this right here was stored as sort of like as a struct, essentially.
So you're just guessing.
We're guessing checking here, and then this specific print string essentially just gives away like the structure of that struct. I'm also going to try going a little bit faster from here on out, especially because like we're running a little short on time. One thing is there's things called virtual tables. So C++ gives you things called classes, and they will, if you have like virtual functions inside of classes, it gets really annoying because you have to load that into your heap memory. If you go to the assembly meeting, you'll understand that better. And essentially, what if they're like the get or like damage player function was a virtual function instead of a C++ class? You can't actually directly like hook that function using like traditional methods. You actually have to find that function in the heap first, and then we can actually find the function that's in the heap and then hook it from there. So Windows adds this thing called RTTI metadata to all of its like binaries. So if you ever create a class inside of Windows, then it adds this metadata, and essentially your Ghidra or Binary Ninja can take this metadata and rename specific parts of like your binary to make like reverse engineering a lot easier, because you'll see like, okay, how are classes sort of structured in that binary. So DLL injection, traditionally, right, we'll use this function called load library and create remote thread. So from a high level aspect, if you want to look later, you can look into the template repository that I posted on PwnyCTF. But essentially what we're doing here is that we're forcing a program to, like, after we write the DLL that we want to inject into memory, or that we want to inject into the process's memory, we call load library on it. So the program actually is able to like read specific functions from it and actually like loads our DLL. And then we use create remote thread to actually run the entry point of our DLL. So we can actually like have specific part, like so our DLL does stuff, right? We're calling like the main function, for instance, in our DLL. And there's also a thing called manual mapping. It's a lot more stealthy. I won't get heavily into it, but essentially you can't just like, the program has to actually like scan memory to know that a DLL has been injected. It can't just go down the PEB and see like, okay, what DLLs have been loaded into memory. And right here is like the DLL main, like the entry point to a DLL's function, or like that's the main function. Did you have a question? Or okay. So hooking functions is essentially in assembly, right? Let's say that this is like the start of a function. Right here, this is the first instruction in there, second instruction in there. What we'll do is that we will essentially, with these two first lines, is that we are putting this to go to our own code. So immediately when this function is called, we are jumping to an address, right? That is our own code, right? Like a function in the DLL memory with our code in it. And that allows us to do like the techniques that I was explaining earlier. So instead of our hook, we'll do like our processing and whatnot. But what we'll have to do is that we'll have to actually call those first instructions that were that we replaced, because we're replacing the instructions from the top here. So we actually have to call that. So our program just does, or like it expects specific values to be in specific registers. If we're not pushing specific values into there, that's not expecting, it'll likely crash. So we have to call the operations that we replaced and then go back to the specific function that we're trying to hook. Does anyone have like any questions about that? So essentially the reason why this instance, it would be like the reason why we're calling the function back after that is that like the executable program expects it to run. And if we don't return anything from that, or it has an unexpected result, the game might just crash. And then again, there's like some really popular like modern hooking libraries that allow like, you don't actually have to manually write this inline, because you'd have to write inline assembly to do this, which is very, very tedious. So there's libraries that allow you to hook functions a lot easier without having to write inline assembly.
You have to like set the allocation memory, because if you're inserting like your own function, and that's like,
so you have your own function which is stored inside of your DLL, right? And then
you already have.
Yeah, it's already allocated in memory. Essentially, all we're doing is that we're patching out the binary, like in memory, we're patching out the binary to point to our code, and then we point back to their code. So one example of hooking that made this really nice. So if you're ever like wanting to like make like cheats where you can see through walls, maybe you want to like overlay something external in that process, right? So that is like if you wanted to like see through walls, but you didn't want the game to know that you're seeing through walls, you can just render an overlay over the game showing like the player locations. So this is sort of a proof of concept, but you can use OBS, and I hooked like the point where it's like actually rendering out like your preview screen, and I'm able to like modify the individual pixels on that buffer, and then I am jumping back to their code to finish rendering that. So essentially over like this, right? It's taking a snapshot of my screen, right? Calling this function to actually render it. I'm hooking it, modifying the actual like image that's going to be rendered, and then letting it continue. So it renders this red square on top of what's already there. And this allows us to create like overlays for like seeing through walls. Yes. Very, very little. Very, very little. It's actually very efficient. It's DX. It uses DirectX, so it's all like GPU accelerated. So that's why it's like very fast. There's one method called return address checking. And essentially what this is, from a high level, is that we're checking if a specific function, right? If we're like, our return address goes back to a function that called it, right? So essentially what we can do is that we're checking if, okay, someone called this function here. Is the person that is, or is this function in our memory or is it in some DLL's memory? So essentially what this is in here, this is some pseudocode extracted from Roblox, is that what they would do is that they check if their return address is like where they would expect it to be, right? So is the function that is calling this current function like legitimate? Is it in a memory and not the DLL's memory? We can just bypass this by patching this and knopping this branch. Yes.
I've never seen anybody bypass this by patching. So what's the change when you're doing this or doing stacks both?
This is
Stacks.
you can just usually you can just knock these, right? And then usually the method you go is that you patch your integrity checks and then you just knock the return address checker,
Okay.
or you patch it out to jump to after the return address check.
Okay.
And then speaking of integrity checks, what programs will do is that like if you have like a player struct or whatever, right? Or not necessarily a player struct, or if we have a function, right, that we don't want people hooking, we can take a snapshot of like that specific memory region and then hash it, right? So then we have a specific like unique number that represents that memory. And if that memory is ever to change, then the hash wouldn't match anymore. So essentially, we're checking to see if like stuff, essentially what this is, it checks if people are patching out binaries or applying hooks, because applying a hook actually patches the binary in memory. So we're checking if the actual code section of our program is still like legitimate, if it hasn't been tampered with, is what this is doing. And one funny thing, I didn't get to implement this challenge, right? It was a little heavy on time, but you can actually have integrity checks that check each other, so that when you patch one integrity check, another integrity check like makes sure that like it like detects that and it's like, okay, dude, what the heck? We're not having that. So one way to get around this is trying to race out like the integrity checker, like maybe it runs every 0.5 seconds. You want to just race it to instantly patch out everything before I could even check another function. That is very inconsistent. So another better way to do that is something called using hardware breakpoints, which I'm not going to really delve really deep into here, but there's a method of hooking using a hardware breakpoint that doesn't actually patch memory, and you can use this to bypass this, and like you can just make it like always return the correct hash. Bypassing signature scans. So right here, this is like a non-vectorized pattern finder. And programs, again, they'll just go down their memory list and see if like your program is loaded into their memory. So what we can do to bypass this is, I think Ronin has a lot more sophisticated methods, but we do a thing called like virtualization, which is like a common obfuscation technique where we're sort of like creating like a specific new computer architecture, right? That's running like virtually. And that's sort of like your program's running in a different language than just regular x86 64 assembly. And then that's all like the higher level that's actually running that like other languages code is in x86 64 assembly. So essentially you're just running a VM, or you're running it in a VM, and it's really hard to like, it makes your code really hard to reverse engineer. You can also shuffle your structs, like maybe they have a signature on like one of your structs you're using in your program. You can just like shuffle like them around, and it'll all just calculate based off of like your offsets, right? And it'll still compile because you're querying or like you're indexing a struct by its actual name. Yeah, and then trivially to bypass this, you just hook the signature scans. I mean, that's like the meeting flag, right? Just hook the checks. So modern anti-cheats run a little short on time, but they run in ring 0 in the kernel mode, and they have access to the entirety of your computer's memory. So they can they really, if they want to, they just go down all your processes and scan the memory of it for signatures. These are usually like the modern anti-cheats are like heavily obfuscated, and they also encrypt memory, and they're very invasive. So they like literally run when your computer boots up, right? It's a rootkit, and they just like continuously monitor your system to see, are you loading cheats even though you don't have my game open? Which is like, if you ever heard of Vanguard, I don't think it does that, but like people are like suspicious that it does, because it totally could if they wanted to. And also one thing is that kernel anti-cheats can actually monitor kernel callbacks. So they just know when you're performing a syscall, and they can just like absolutely detect you if you're like trying to like write specific parts of memory. One way to like fight on the same level of this is that you also have another driver that's also just as privileged as your kernel anti-cheat, and you can read and write memory, same privileges as your kernel anti-cheat. One thing about this is it requires a code signature. So like, unless you're like a multi-million-dollar company, Microsoft isn't just handing out driver signing certificates. Actually, it's like $300. I lied. It's like $300 to buy a driver signing certificate. You can like, yeah. You can also just like steal NVIDIA's signature, and that works. But the way that we bypass these kernel anti-cheats with another driver is that we just load before that anti-cheat, and then I think, do you guys know what the meeting flag is? We just hook all their checks, and then there's nothing they can do, right? Unless you're using side channel attacks, and that just kind of sucks.
If they start at startup, how do you beat that? Because if you also have your cheat and startup, then it's not going to be.
Yeah. So that's the hard part, right? You have to find out a way to get your driver to start before, and sometimes it's random, right? Or sometimes it's like indexed and like maybe like alphabetically, right? There's specific ways to get your driver to load before, and then you have a very small amount of time though to actually like hook the checks in the anti-cheat. You can also I won't get into it here, but like you can delay the anti-cheat loading for a bit and load your driver before that. There's a method. I'm not too sure about that. I haven't actually performed it myself, but you can actually like delay the anti-cheat loading, and then load your driver in first, and then patch all of the anti-cheat checks. My personal favorite method of game hacking is through a kernel-based virtual machine. So this runs in ring -1. So you actually just have access to virtualized memory. So a lot of anti-cheats will, like Vanguard, for instance, if you guys play Valorant, uses like like they abuse VBS and virtualized based security so that your kernel driver can actually read its like that specific memory. So if we're running in a KVM, we just have full access to all of that memory. And we can also just like read and modify guest memory without it detecting, because like we control the memory. So essentially the whole goal here is that we run the cheat in like our host computer, and then in a VM we're running the game, right? And then that VM, we're just manually modifying the memory of the game without any syscalls or anything. Very detectable to detect if you're in a VM. You can check your CPU ID flags, see if like your CPU frequency is always at 1 gigahertz for whatever reason and never changes, or sort of like if you have a hypervisor present. System management mode. All right, this is where we get real absurd, right? So if you remember our kernel, which was ring 0, right? We can go even deeper, and we have this thing called system management mode. Okay, this is the most privileged system you can get, right? If you have this, you have more than just a rootkit. You have, if you can arbitrarily remotely install this on someone's system, it's just over, right? You just win. So essentially what we can do is that this is triggered by like hardware interrupts. So like like a moving a mouse event through a USB can like trigger SMI, and then your CPU goes into the special mode that's really privileged to like process like the hardware input like from your mouse and such, and then it goes back to the operating system memory. But in that time, we can requires you to write to your own BIOS using a BIOS flasher, right? So like you just have to like overwrite your BIOS with some open source BIOS and then write your own system management mode module to accomplish this. But what I have been able to do, right? So you can actually just read memory. It's a little more complicated in that you're usually limited to system management mode RAM, but there are ways to get around it using like a custom module. So essentially what happens and what I've applied before is that the system management interrupt is triggered on like a USB mouse move event, right? And then from there, our CPU is now in system management mode. We read the game memory at that specific point, and then we spoof, right? Like, because like we're in between, like, okay, what is our actual operating system seeing, and what is our actual hardware doing? We're actually telling our system that, all right, our mouse is moving in some different way, and that different way is just towards another enemy's head, right? So it's just an aimbot based off of this. Anti-cheats can't scan system management mode memory, so like your process, like you are below the hypervisor. They can't do anything to like signature scan you or anything. It's vulnerable. I've never seen like it not have false positives, but is vulnerable to side channel timing attacks. I think Vanguard has been beginning to implement side channel, like detecting how many times specific addresses have been read, which is so scuffed. But
How does that?
what do you mean? Or sorry, how does what work?
What's the side channel? Like, what do you say?
So like if you can't really like ask me about it, but you might be able to ask someone else. But so essentially, like you can measure like the delay between specific instructions being called and like assume what's being happening on like other processors, or for instance, or like you can leak memory, or like you can leak specific information. I don't really know much about it, but generally it's just like a really like stupid way to just like detect when memory is being read. It also has like a lot of like false positives, and also mostly now you can just use like, if you're getting down to that point, they're just going to use like AI detection methods on your statistics, or like other heuristic detections. Direct memory access, it's a little less sophisticated than SMM, but essentially just have a PCIe card plug into your computer that can directly read and write like the parts in RAM. And this is like because this actually runs in it's less privileged than your in a ring that's less privileged than your hypervisor. So you can't actually read virtualized memory using DMA. And also like the IO MMU prevents like DMA from reading specific virtualized pages. So that's why like Vanguard will like have you enable IO MMU and virtualized base security, because it'll essentially just prevent you from reading any of Vanguard's memory if you have these two things enabled, which they require you to have. This also requires you to have FPGA firmware development skills. And if you don't know what that is, you should look it up, because it will make you rich if you go into it. And if you have FPGA development skills, you have better things to do than hacking games, okay? Here's an example with Valorant. This used DMA. And we essentially read and decrypt the player positions from Vanguard, because they store their player like positions in Vanguard virtualized memory, which is or in this case, we have a method to get around virtualized base security through specific like flag spoofing, but it got patched a while back. We can just decrypt memory from Valorant, because they do encrypt their like player positions, and we do a little bit of trigonometry, and then we render a specific overlay that shows us where all the players are through the walls. AI cheats are a lot more sophisticated method of cheating. And so essentially what you have is that, I have done this before, you have a capture card on a second computer that's just reading the screen that you have on your main computer, and you're processing that in a YOLO model that detects all of the enemies and their heads, and you send that information through a microcontroller through like like the serial port on it. And that microcontroller can be like spoofed as a hardware device or like any mouse. And you can just essentially like have an aimbot and it's completely undetectable unless they do like heuristic detections on your specific microcontroller. Yes.
What is YOLO?
YOLO is like a convolutional neural network that like essentially what it does is that it will give you bounding boxes of specific things that it recognizes and label it, right? So like it will like if we used YOLO on here, it could like put a box around this chip and say like microcontroller. It'll label it, yes.
Well, I heard to do all that SNAP shit.
This is like very like I hate to say, but the biggest like detection vector here is through your microcontroller, right? You can detect like, okay, what if I try writing some mouse firmware, or like what if I try like restarting this microcontroller? Then it will go into like a specific mode where it's like, okay, program me, right? Like no normal mouse is gonna go into like open up a UART or like a COM port, right, to be programmed right after it's booted. So they'll just like Vanguard will just reboot your mouse to check if like you're using a microcontroller.
Like say you have like a mouse that you can't figure out.
Yeah. Then the other detection is that they can detect you're using a capture card to like record memory, which is like if you spoof your EDID, it's like theoretically this is like
What if you're streaming though?
yeah, that's exactly like that's like what usually works. That usually works. But yeah, this is kind of like it's between like I think you can become it's a lot easier to code AI cheats, and this is probably like the future of most cheats are going to be because nobody is writing system management mode modules and flashing their BIOS just to cheat in a video game. Like I was just like, I did it for fun. I also just had like an old computer to brick for whatever reason. So that's why I did that. Also, honorable mention because Henry asked me to. You can code C# and mono game cheats. All of this stuff right here is for like C++ games, but you can actually like C# is interpreted language. You can decompile it almost exactly down to the source code. And you can actually do like direct intermediate language patching use mono CSIL for assembly modification. So you can like patch like your C# assembly in memory. Mono injector just injects your C# code. And then Unity, I don't really know about this. This was on Wikipedia, but I think with Mono you have access to the Unity engine API, but then you don't with IL2CPP, or I forgot what this was. But then no signature scanning is needed to like find like specific like functions. You can just use reflection to find specific methods that are in the program. I think Ronan would probably know more about that, like reflectively.
Yeah, I mean, I mostly use reflections just to see wireless.
Yeah.
You can do it. I'm a little skeptical on the detection side, but
Yeah. And then since we're like already over the meeting time, there's advanced reverse engineering techniques. You can unpack like Vanguard packs their binaries. You have to load it into memory first and then take a memory snapshot of it to dump their unpacked binary to reverse engineer. You can devirtualize by lifting a specific binary to LLVM IR that requires a little bit of programming. But once you can do that, tools like Binary Ninja can fully decompile it from there. And then BinDiff is a really nice tool that if a game updates, its addresses change, and you'll have to like find those new addresses. And if you use BinDiff, it makes finding the new addresses in the game a lot easier because you're able to just essentially diff two binaries. Here's some resources. The slides are posted on the meeting. And then if you guys, anyone wants to stick around, I'll show you how to set up like an environment to set up your cheats and stuff. So, and it's time to social, Rubber Ducky, and then SIGPwny with SIGArch. And here's the meeting flag again. Awesome. Yeah. So I'm gonna end the meeting right here.